In this video, we're going to be analyzing some of the thermodynamic aspects of one of the pericyclic reaction. This is a cycloaddition. Why? We're adding this molecule to that molecule. This is a diene in the SC's conformation, and that is we call a dienophile. In the process, all of the pericyclic reactions happen through a cyclic transition state, and that following the movement of the electrons shown in the arrows, we get that product. So analyzing what's going on in forming and breaking reactions is going to allow us to predict the sign of delta H. And we're going to be talking also of the sign of delta S. So first of all, let's talk delta H. If we see in molecules A and B, if we analyze that, we have total 3 pi bonds. And here I have 1 pi bond in the product. What that is that the net change, say in pi bonds, is 3 minus 1 is 2. So we have that change. And we need to put in energy enough to break 2 pi bonds. So see, I'm going to erase that. So the net change, I'm going to write it better. The change is 2 pi bonds. I need to put in energy to break 2 pi bonds. Overall, yes, I have involved 3, but I'm forming 1. Remember that when bonds break, to break bonds, we put in energy, so heat is added. And so, when bonds, so energy, let's say in, absorb, you need to put in, and when bonds are formed, energy is released. In the form of heat. This implies energy in if you need to put a delta H greater than 1. So endothermic process. When bonds form, energy is released. That is an exothermic process. All right. So the balance in pi bonds is net change is I need to break 2 pi bonds. So that part there is endothermic. But that's not the only thing that's happening. We are forming 2 new sigma bonds. So 2 new sigma bonds that were not there. So now, forming sigma bonds, that is energy that is released. Forming bonds release energy. So overall, even though I had to input energy to break through 5 bonds, this delta H is going to be smaller than the energy that is released. Again, this being stronger bonds, there is more energy released than the energy that I need to put in. So what is the balance when we counter C? So more released than I need to put in. So overall, the reaction is exothermic. So more energy release. So delta H of the reaction is negative. The reaction is exothermic. That's in regards to the enthalpy, because again, the key concept is to remember that to break bonds, you need to put in energy, and that when bonds form, energy is released. And since you're forming 2 stronger bonds, compare sigma to pi bonds, then energy overall is released. Now let's talk about the entropy part of that. Remember that when we talk about spontaneity of reactions, we work with delta G, and delta G, remember, give free energy equals delta H minus T delta S. So we have talked about this portion. So the reaction so far, the reaction is exothermic. So let's see what happens in terms of the entropy. In terms of entropy, here you have 2 molecules A, B combining to give 1 molecule C. So the number of molecules has decreased. So less translational degrees of freedom. So when we have that less number of molecules, the overall entropy of the reaction is decreasing. So I'm going to write that down. Delta S of the reaction is negative, is decreasing. So let's see now overall what that change will be. Now I'm erasing this part to do that analysis based on that equation that says that give free energy to determine spontaneity, right? Give free energy equals the change in give free energy equals change in enthalpy minus T delta S. And we have determined that because more energy is released when forming sigma bonds, that the energy that I need to use to break 2 pi bonds overall, we have determined that this term has a negative sign, so the reaction is exothermic. I know that that's negative. Now, the reaction also has a decrease in entropy because there's less number of molecules, so a negative here. Now, this term is negative times a negative. The second term overall is positive. I know for the reaction to be product favor, I want this to be negative. So negative is an exergonic process. So that means product favored. But now I have this term is negative and this term is positive. So I need this term delta H to be bigger than the other term. So to ensure that these reactions are carried out at low temperatures. Because that way you are minimizing this term, so the T delta S term is going to be smaller, and when you add those up, the predominant factor will be the enthalpy. So at low temperatures, these reactions, these cycloadditions, and addition reactions in general, because they involve a decrease in entropy, they are favored at low temperatures. Now, these reactions, we're going to see later, can also be reversible, and in fact, this can break if the temperature is higher. This particular reaction with this diene and this dienophile is called a 4+2 cycloaddition, and we also know that as Diels-Alder addition. So at low temperatures, we're favoring the cycloaddition, the Diels-Alder. If the temperature is higher, this